Alright, so in this video I'm going to be explaining another important article about domain adaptation, and the title of this article is Optimal Representations for Covariate Shift. So this paper in 2022 from Vector Institute. Machine learning systems often experience a distribution shift between training and testing. In this paper, we introduce a simple variational objective whose optima are exactly the set of all representations on which risk minimizers are guaranteed to be robust to any distribution shift that preserves the base predictor, for example, covariate shifts. Our objective has two components. First, a representation must remain discriminative for the task. For example, some predictor must be able to simultaneously minimize the source and target risk. Second, the representation's marginal support needs to be the same across source and target. We make this practical by designing self-supervised objectives that only use unlabeled data and augmentations to train robust representation. Our objectives gives insight into the robustness of CLIP and further improve CLIP's representation to achieve state-of-the-art results on domain bed. It is hard to build machine learning systems that are robust to distribution shifts between a source and target domain. One promising approach is domain generalization, is learning robust representation from which predictors trained on source must perform well on the target. In practice, however, no current domain generalization method for learning representation uniformly outperform empirical source risk minimizers. Our theoretical understanding of DG is still lacking. We introduced the first simple variational objective whose optima are exactly the set of all representations on which source risk minimizers are guaranteed to generalize across distribution shifts that preserve the base predictor. We work on idealized domain generalization that we assume that the learner has access to the source population risk. By the way, this paper is about just single source, single target. And when it says domain generalization, you want to see what happens on the target. And we don't have any label like any other thing for the target. This means that any optimal representation learning method must seek discriminative information about target. Even worse, we prove that without access to some knowledge about a target, any representation learning algorithm cannot uniformly outperform a constant representation, which may explain why domain generalization methods struggle to outperform ERM. So we provide minimal sufficient objective whose achieves optimal domain generalization under covariate shifts. We prove that it is impossible to learn useful representations without accessing target information. And we provide practical objectives to learn optimally robust representation. So we are interested in predictions that are robust across distribution shifts. We formalize this using domain generalization language. So given a distribution over inputs and labels y from the source domain, so D is source domain, we select a predictor f, this predictor f, and the predictions could for example be labels for distributions over labels. Despite being selected on the source domain, we would like f to achieve a small expected risk with respect to loss function on a distribution from a target domain, which is somehow related to D sub s. A common strategy is to learn robust representation, which splits the problem into two. First, learn an encoder which maps inputs to representation Z, then learn a predictor from Z to gamma from representation to labels using standard risk minimization. The goal is to design a robust representation. So this Z, so that the predictors H trained to minimize the source risk also achieve low target risk. So the idealized domain generalization risk of an encoder is the expected over domain. So this expectation is over domains. The worst case over source risk minimizer target risk. And H is the argmin of R are the source risk minimizers. And P is any joint distribution that has full support. So we call representation Z star and its encoder optimal if it minimizes the IDG risk. So it's an expectation of supremum of these risks. Note that we are conditioning on this Z, this latent variable. Because as I showed that we first give a map that we go to Z, and then from Z we go to gamma. So these are the assumptions. All domains we consider are related by the following assumptions. Generalized covariate shift, all domain-specific risk minimizers are equal to the Bayes predictor under support. And invariance of Bayes predictions, the set of Bayes predictions is the same for all domains. So you see in this figure, the optimal representation for IDG must have invariant support while being simultaneously discriminative on all domains. But B says that without the discriminative requirement, a source risk minimizer can mispredict the target. And in C, that we say that without support match, some risk minimizer will perform poorly. And the intuition behind our objective is that under this generalized covariate shift, any source risk minimizer will make optimal prediction on target samples that are also in the source. Because this generalized covariate shift ensures that F star is simultaneously optimal on all domains. That's why we call it distributionally robust. It means that overall kind of domains that you can go over all of them, it satisfies. And under our assumption, an encoder is optimal for idealized domain generalization if and only if it minimizes the risk, this infimum of expectation of risk, while matching the support of Z across domains. Moreover, such encoders exist and their IDG risk is the Bayes risk. Our characterization of optimal representation requires labeled data from all domains, which is impractical. And we show that this can overcome with self-supervised learning, which is a technique for training representations without direct access to labels and a particular class of data augmentation. For example, in clip images, or images are augmented with all text collected on the internet, and invariance is enforced between representations of the image and its text pair. For example, its text pair is a dog with floppy ears. It's the dual of that. It's a pair, so just image and the text. So more precisely, an augmentation is a random variable sampled conditionally from the input X. The key requirement is that augmentations retain task information. Specifically, if any samples X and X prime have the same augmentation conditional, then their base predictions must be the same. Our first domain bottleneck minimizes this I, which enforces support match using a KL divergence. Dropping constants with respect to Z, we thus aim to maximize edge, and domain adversarial neural network does so by ensuring that a domain classifier cannot predict domain from representations. To overcome these issues, we construct this Q of D conditional Z without introducing additional parameters and with a bound that is tight with enough samples. And we set our variational distribution to the expectation of P hat, where Q is a contrastive variational distribution constructed with samples X. So the final loss is just this expectation. Our second domain bottleneck is the entropy bottleneck that minimizes this H, where the first equality uses encoder's determinism. Int enforces support match by removing all information that is not needed to maximize the mutual information between Z and A. In particular, minimizing I is more stringent than mutual information between Z and D, and as it also matches representations inside the domain. The advantage of Ent is that it does not require domain samples, which are rarely accessible in self-supervised learning. We consider the standard variational bound used in neural compression, where the entropy model Q theta is used. So this loss of entropy bottleneck is just the expectation of this. So A shows the adding bottlenecks significantly improve worst case domain generalization performance and using domain agnostic augmentations performed as well as with labels. But in B, we see increasing the domain bottleneck weight will improve target performance until it decreases source performance. And in C, we see that domain agnostic augmentations are crucial, but approximate domain adaptation, domain agnostic might also be sufficient.